Hello everyone, I'm Saishnu Manohar from CSCB, presenting my concept video for linear algebra and calculus. Topic I've selected for my concept video is finding powers of a matrix by using Cayley-Hamilton theorem. Let's begin. Let's get along with the introduction. A matrix is a rectangular array of or symbols arranged in rows and columns. Matrix multiplication is a fundamental operation in linear algebra. Finding the powers of a matrix is important in many applications, such as modeling physical systems, data analysis, and machine learning. The Cayley-Hamilton theorem provides a powerful method for finding powers of a matrix. Let's get along with an overview of Cayley-Hamilton theorem. The characteristic equation of a matrix is a polynomial equation whose roots are the eigenvalues of the matrix. The Cayley-Hamilton theorem states that every matrix satisfies its own characteristics equation. This means that we can use the characteristics equation to find powers of the matrix. Deriving the Cayley-Hamilton theorem. The Cayley-Hamilton theorem can be derived using the theory of polynomial rings. We can define a polynomial ring R of X, where R is a commutative ring and X is an indeterminate. We can then define a polynomial f of X in R of X to represent a matrix. Using the properties of polynomial rings, we can show that f of A is equal to 0, where A is a matrix and f of X is the characteristic polynomial or the characteristic equation of the given matrix A. Example for applying the Cayley-Hamilton theorem. Consider the matrix A is equal to 1, 2, 3, 4. Then the characteristic polynomial or the characteristic equation of A is f of X is equal to x squared minus 5x minus 2. Now using the Cayley-Hamilton theorem, we can write a squared minus 5a minus 2y is equal to 0, where we just replaced x with the variable capital A, where A is the matrix, where I is the identity matrix, I is nothing but 1. This equation can be rearranged to find a square in terms of A, which allows us to find the higher powers of A. Now coming to the main topic of our PPT, computing powers of a matrix using the Cayley-Hamilton theorem. Given a matrix A and its characteristic polynomial f of x, we can use the Cayley-Hamilton theorem to write a power n as a linear combination of a power k, where k ranges from 0 to degree of f, which is the degree of the given characteristic polynomial, and degree f minus 1. We can compute the coefficients of this linear combination by using the initial values of a power k, for k is equal to 0 and degree of the characteristic polynomial or the characteristic equation minus 1. This method can be used to efficiently compute I powers of the matrix. Now, coming to the examples for computing powers using Cayley-Hamilton theorem. Let's begin. Now, let's look at a problem. Suppose given matrix 1, 2 and 3, 4. One second. And other matrix and if 1, 2 and 3, 4 is equal to A, then the given characteristic equation is x squared minus 5x minus 2 is equal to 0. Now, in terms of characteristic equation of the given matrix, we can write it as a squared minus 5a minus 2y is equal to 0. Now, 0 is equal to a squared minus 5a minus 2. And from here, we can write a squared as a squared is equal to a squared 5a plus 2. Now, let's multiply both sides by a. We get a cube is equal to 5a squared plus 2a. Now, taking 5 from common from the equation, we get 5 of 5a plus 2 plus 2a, which gives the final result of a cube as 27a plus 10. Since you are finding the fourth power, multiply the expression by a again, which is the common thing to do. Now, multiplying the given expression with a again gives us a power 4 is equal to 27a squared plus 10a. Now, taking 27 common from the given equation, we get a power 4 is equal to 27 of 5a plus 2 plus 10a. A power 4 is equal to, if you multiply 27 inside, we get 145a plus 54. What does it mean? Remember, so that the constant is multiplied by 1. So, as we know, the constant I is nothing but the 2 by 2 matrix of an identity matrix of the order 2 by 2. Now, we know in the starting the assumption thing that a is equal to 1, 2, 3, 4. Now, substitute those values in the resultant equation of a power 4. We get a power 4 is equal to 145 of 1, 2, 3, 4 plus 54 of the identity matrix 1, 0, 0, 1. Now, multiply inside and add, we get the final output as we desired. A power 4 is equal to 190, 290, 435, and 634. This is how we do it. Let's go to the next example. Suppose the given matrix is similar 1, 1, 2, 3, 4, and P of lambda is equal to det of lambda I2 minus A. Suppose P of lambda is det of lambda minus 1, minus 2, minus 3, minus 4. We get the characteristic equation as lambda square minus 5 lambda minus 2. Now, the Cayley-Hamilton theory states that P of A is equal to, replacing lambda with the variable a square minus 5a minus 2i is equal to 0. Now, 0 is equal to a square minus 5a minus 2. Now, multiplying both sides by a minus 1, a power minus 1, which is nothing but a inverse. 0 is equal to a minus 5i minus 2 a power minus 1. Now, moving to a power minus 1 to the left hand side, we get 2a power minus 1 is equal to a minus 5i. Now, substitute the values of a and I in the given equation and put the 2, bring the 2 back to the RHS. Now, into multiplied by 2 becomes divided by 2. So, the final equation is a power minus 1 is equal to minus 2, 1, 1.5, and minus 0.5. Next example. Cayley-Hamilton theorem. Using Cayley-Hamilton theorem, verify that the given matrix satisfies its own characteristic equation and find a power 4. Solution. Once you find the characteristic equation, which is lambda square minus 6 lambda cube minus 6 lambda square plus 8 lambda minus 3 is equal to 0 by Cayley-Hamilton theorem, just a cube minus 6a square plus 8a minus 3i is equal to 0, just replacing lambda with a. From the given matrix, finding a square, substitute the given values on the respective positions, and we get a square and a cube. Now, as soon as we get a square and a cube, substitute those values in the given Cayley-Hamilton theorem characteristic equation. Now we get a final output. Now, for getting a cube and a power 4, just multiply an a on both hand sides. Suppose a cube is if you want to get a power 4, just multiply 6 so that we can get the desired output. Now as we got a power 4, which is nothing but 124 minus 123, 162 minus 95, 96 minus 123, 95 minus 95, 124, which is the desired output. We needed to find a power 4 and thus we find it. Hence proved. Now here is a small example, another small example of the Cayley-Hamilton theorem and powers computing. You're given a matrix, verify that it satisfies its own characteristic equation and find a power 4. Now, the given solution, we know the characteristic equation is lambda square minus 5 is equal to 0. From by Cayley-Hamilton's theorem, a cube minus 5i is equal to 0. From the matrix, find a square, nothing but 5005. As we know, I value is I1001, an identity matrix. Now multiplying with a power 4 gives us a power 4 minus 5a square is equal to 0. And a power 4 simply becomes 250025 because we're just multiplying 5 with again 5 of identity matrix. Here is another equation. Just look at it. Now we'll move on to the next one. Now let's move on to the applications of Cayley-Hamilton theorem. The Cayley-Hamilton theorem has many applications in linear algebra and beyond. It can be used to diagonalize matrices, compute exponential functions of matrices, and solve differential equations. It is also used to control theory, signal processing, and quantum mechanics. Limitations of Cayley-Hamilton theorem. The Cayley-Hamilton theorem only applies to square matrices. It's a big limitation. It does not provide a method for finding the eigenvalues of a matrix, which must be computed separately. It is not always the most efficient method for computing powers of a matrix, especially for large matrices. True. Let's get on to the conclusion. We have come to the end of the PPT. The Cayley-Hamilton theorem is a powerful tool for finding powers of a matrix. It is based on the characteristic equation of the matrix and provides a simple and elegant solution to the complex problem. The theorem has many applications in mathematics, engineering, and science, and is an essential tool for anyone working with matrices. References: Horn, Roger A., and Charles R. Johnson, Matrix Analysis, Cambridge University Press, 2012. Leuenberger, David G., Introduction to Linear and Nonlinear Programming, Springer Science and Business Media, 2015. Friedberg, Stephen H., Arnold and Insel, and Lawrence and E. Spence, Linear Algebra, Pearson, 2014. Boyd, Stephen, and Levin van Berge, Convex Optimization, Cambridge University Press, 2004. Strang, Gilbert, Linear Algebra and its Applications, Cengage Learning, 2015. Thank you. Thank you for spending your valuable time with me. I hope you enjoyed my presentation. This is Aishto Manohar presenting my concept video for the subject Linear Algebra and Calculus. Thank you. Thank you very much.